Welcome back, everyone, to the Algebraic Graph Theory Seminar. This week we have Lord Kavi, and he'll be talking about the k-independence number.
Thank you, everyone, for coming. This is a work I'm doing with Mike Newman. I'm from University of Utah. So my name is Lord Kavi. I'll be talking about the k-independence number. And so I'll quickly go through the main tool for this work, eigenvalue interlacing. And please pardon me if it's something trivial to you. I just have to fulfill all righteousness. And then I'll talk about the interlacing theorem and then the independence number and how it's generalized to the k-independence number I'll be talking about. This work is heavily based on the work by Ida, Gabriel, and Mika. So first of all, let me start by explaining with an example. So let's consider the adjacency eigenvalues for the cycle graph on 4 vertices. This is 2, 0, 0, and minus 2. And so if we also look at that of the path graph, the adjacency values of eigenvalues of the path graph on 2 vertices, that's root 2, 0, and minus root 2. So we can see a pattern where the eigenvalues of the adjacency matrix for C4 can be written in relation to that of the P2 like this: 2 greater than root 2 greater than 0, 0. So basically what we are saying is that these values interlace these other values. Right. So that's the whole concept of interlacing. More formally, if you consider a sequence, 2 sequences, mu1 to mu k and lambda1 to lambda n, which can all be ordered, and k less than n, then we say the first sequence, the mu sequence, interlaces the second sequence if we have this relation, lambda I greater than mu I, and mu I also greater than lambda n minus k plus I for all i's from 1 to k. So for instance, if we have, as in the example before this slide, if we have k to be n minus 1, then interlacing strictly means we can just basically interlace these values like lambda 1 greater than mu 1 greater than lambda 2 greater than mu 2 in that order. So let's give another example. When we have n to be 5 and k to be 3, then basically interlacing means that lambda 1 is greater than mu 1 and mu 1 is greater than lambda 3. And lambda 2 is greater than mu 2 is greater than lambda 4 in that order. So basically this is the idea of interlacing. And this is really a very powerful tool, and it has several applications. It has led to solve otherwise difficult problems. And basically, he has popularized this idea, especially with relation to graph theory. Okay, so we'll look at the interlacing theorem. For the purpose of my presentation, there are some other, maybe 2 things to be added, but for the purpose of this presentation, I'm going to ignore those other 2. Now, basically, if we have M to be a real symmetric n by n matrix, this can also apply if it's Hermitian. And we also have an R matrix, an n by k matrix, such that if we take the product of R transpose by R, we get the identity matrix. Then we form a new matrix from this R and our M by multiplying R transpose times n by R. Then this new matrix we formed, N, the theorem says that the eigenvalues of this new matrix N interlaces the eigenvalues of the original matrix M. And if the eigenvalues for the M matrix, let's suppose it's lambda 1 to lambda n, that of n is lambda mu 1 to mu k with their corresponding eigenvectors v and ui's. If it happens that at any point in time ui equals to lambda I, then what this means is that there is an eigenvector u which corresponds to the eigenvector of this eigenvector of this eigenvalue, such that we are able to get the eigenvector, the corresponding eigenvector of M. How do we do that? We just multiply the U, the vector U, pre-multiply the vector U by the matrix R. These are R matrix. And so when we know the eigenvalue for eigenvector for the N matrix, we are able to get the eigenvector for the bigger matrix. Now, two immediate consequences of this interlacing theorem. The first one is the principal interlacing theorem. If we take R to be this matrix, then our N matrix that we are forming is a principal submatrix of M. So basically what this tells us is that so using the term, the principal submatrix, the eigenvalues of the principal submatrix interlaces the eigenvalues of the main matrix. And so when we apply this to graph theory, basically what we are saying is that, for instance, if you have the induced subgraph of another graph, the adjacency matrix of that induced graph is a principal submatrix of the original graph. Therefore, if we know the eigenvalues of any induced subgraph interlaces the eigenvalues of the main graph. A second application of this has to do with quotient matrix. Let me also explain this with an example. So let's consider this matrix A, and let's partition this matrix as here. The quotient matrix is basically the average row sum of each of these blocks. So first of all, we partition the matrix using a particular order, and then we find the average row sum for each of these blocks. So for instance, if you consider this block, the sum is 1. So now divide by the total number of rows we have here, which is 1. So this gives us 1. And this is 2. If you take this block, the sum is 2, divided by the number of rows is just 1. So we have 2 here. Now let's consider this also, this block. The sum is 2, and we are dividing through by the number of rows. We have 2 rows here. So this gives us 1. So basically, this is the quotient matrix. So first, we have to partition the matrix with respect to a particular ordering, particular partition, and then take the average row sum for each of these blocks. And now, in applying the theorem, if we choose R to be this matrix, where P is the characteristic matrix of the partition we've chosen, then B, the B matrix, the quotient matrix, is similar to our N matrix, the R transpose by R matrix. And therefore, the theorem, the corollary of the theorem says that the eigenvalues of a quotient matrix interlaces the eigenvalues of the original matrix. We observe that this matrix is not precisely this, but it's similar, which means they have the same eigenvalues. So now we can proceed to the independence number. So what's an independence number? So we are just independence first of all. We are looking at a set of vertices, no two of which are adjacent. And therefore, when we look at the size of a largest independent set, we call that the independence number. And that gives us, we denote that by alpha. Let me use an illustration. So for instance, we have the Peterson graph. If you consider this set of vertices in the Peterson graph, there's no edge in between any of these vertices. So this is an independent set, right? But at the same time, we can get something bigger than this. We can get this, take any of 2 vertices in the inner and then 2 vertices outside in this order. We found another independent set. And so this is 4 and this is 3. So we see that the independent number is actually 4 for the Peterson graph. So let's look at the generalization of the idea of independence number to k-independence number. So indeed, there are about 2 other definitions for independence number, k-independence number. So, but our focus is this. So consider a graph G, and consider a set of such vertices in the graph such that 2 vertices are distance at least k plus 1. So if you take any 2 vertices in the set, they are at distance at least k plus 1. Then that gives us a k-independent set. And the size of a largest k-independent set gives us the k-independence number. And we denote that by alpha k. Basically, in this set, there are no parts of length less than k plus 1 between any of these vertices. And so if we look at it in terms of graph powers, then basically we are just looking at g to the power k, and then now we just consider the regular independence number of the graph power g k. So we're going to concentrate on how the ratio bound was generalized to the k independence number. So let me quickly remind us of the ratio bound for the independence number. We have a delta regular graph G on n vertices with eigenvalues lambda 1 to lambda n. Then the Hoffman ratio bound, I know that there are some other affiliations of the Hoffman bound to someone else, but so basically the Hoffman bound tells us that the independence number is at most n times minus lambda n on lambda 1 minus lambda n, where lambda n is the least eigenvalue. This proof, this result can be proved using interlacing as well. So for instance, if we partition the adjacency symmetries into U and U complement, where U refers to the independent set, right? So basically what we have is that there is no edge between vertices in the independent set. So all values here will be 0, right? Everything here is 0 because there's no edge. So all the neighbors of U will be in the complement of U. So basically we have 0 over here, right? So now if we are looking at the quotient matrix, for this is 0, so clearly this becomes 0. And now this graph is deregular, so there are delta ones on each row over here, and there are let me call this alpha, so there are alpha rows over here. So each row here we have delta here, and up to delta here, and there are alpha of them. So if we take the average row sum of this, we are going to have alpha delta over the total number of rows alpha. So that gives us delta, right? So this guy is also delta. And now we know that this block here is actually the transpose of this block, is just the same. So basically the total number of edges here is also going to be alpha delta. But now the number of rows here is different. This is going to be n minus alpha. So this gives us, since each row is delta, we can just deduct this from delta, and we obtain this. So the proof eventually now goes back to now we're using interlacing, right? So we know that the eigenvalues of the B matrix should interlace the eigenvalues of A. Now the first eigenvalue here is delta, so we are okay with that. Now the second eigenvalue, we can obtain that using the fact that the trace, the trace gives us the sum of the eigenvalues. So the trace minus delta should give us the second eigenvalue, and therefore the second eigenvalue should be greater than lambda n. And so we'll come back to this. Now let's see how this result was generalized. We introduce some quick notations. G is a graph on n vertices with adjacency matrix A. Lambda 1 to lambda n are the eigenvalues with repetition. Now, if we are looking at distinct eigenvalues, then we'll be using theta naught to theta d. So we have a polynomial, real value coefficient polynomial with degree at most k. And we have two parameters, omega W of p, where W of p is now, if we take the polynomial evaluated at, evaluate the matrix at the polynomial p, then the largest value on the diagonal of the p of a matrix, we'll be calling that W of p. And then also, if we consider the evaluation of the eigenvalues at the polynomial, all of them except the largest eigenvalue, we'll call that lambda p. So this is the minimum, the least value we obtain when we evaluate this polynomial at all the eigenvalues except at the largest eigenvalue. So with these parameters and considering a deregular graph, Ida and Greber and Mikkel came out with this important result that kind of is very important for our work. And this is basically a generalization of the ratio bound. So the condition is that let's make sure that if we evaluate the polynomial at the largest eigenvalue is greater than lambda of p, then alpha k, the k independence number is bounded above by this parameter, this value. Okay. So observe that this bound here is basically a function of p in a sense. So how good this polynomial is dependent on our choice of p, a polynomial p. Let me just give a quick sketch of the proof. So the same, we go for interlacing. So what do we know? P of A, because we are looking at P of A to be a polynomial of degree at most k, then we know that if I take a power of digestive matrix, a power, say A to the power L, this gives us the number of walks between vertex I and j of length L. And so if we choose L to be less than or equal to k, then in this set, this block, any other place is 0, except on the diagonals, because the diagonal, we are looking at closed walks, right? So the up diagonal, everything is 0. Along the diagonal, everything, we have values there. So let's call it P of A subscript UU. That's the diagonal. So what else can we say? Basically, we know that the A matrix, the digestive matrix has equals row sums. That's delta. So if we use, we can therefore know that each row here is going to give us P of lambda 1, or that's P of delta. Right? Each row here sums to P of delta. So if you want to find the quotient matrix, then the average row sum of this is going to give us the sum of the diagonal divided by the total number of rows here. Let's call that R. Let's call that R. So we are going to have this for the first section, first block. And the same with this. So therefore, what we are going to have here is going to be the sum of all this minus this. And therefore, we are going to have this. And this block is transpose of this block. So we can just deduce the rest from this. Right, so with the same idea, the eigenvalues of B interlace the eigenvalues of P of A. And so the first one of the eigenvalues of this is P of lambda 1. P of lambda 1 is an eigenvalue of this B matrix. So we look for the second eigenvalue using the trace idea. The trace minus the P of lambda 1 gives us the second eigenvalue, mu1. Sorry, mu2. And so mu2 is greater than the smallest eigenvalue of PA, which is what we call lambda of P. All right. So we will see that in the trace, we are going to be having this value here. But this value is basically just the average of the largest value over here. But it's difficult. We don't know what the set really is, so we can't be dealing with this. So basically what we have to look for is that this value here is definitely less than the largest, because it's average. This value is definitely smaller than the average, sorry, the largest value on the diagonal, which is W of P. So using that idea, we can now deduce the result, this result from that, and noticing that P of lambda 1 is greater than lambda P. All right. So that's just a quick sketch of the proof. So like I said earlier, the bound depends on an appropriate polynomial. So for the purpose of this work, let's define the best polynomial possible, the best polynomial that will give us the best bound possible from this relation. Let's call it an optimal polynomial. So let's call this bound BP of SP, where SP of G is the spectrum of the graph G. So we are interested in a polynomial satisfying the condition that P of theta is greater than P of theta for all I greater than 1. Basically, we are trying to ensure that lambda P of theta, not the largest eigenvalue, if you evaluate a polynomial, the largest eigenvalue is greater than any other. So we say that this polynomial is optimal with respect to k if it gives the lowest possible bound for alpha k of this form. And one thing we can also observe is that we are basically looking for a closed form formula that depends strictly on the spectrum. And therefore, when we observe this, we want to get a polynomial that for any k at all, we are able to say that, okay, this polynomial, this is the polynomial, and that gives us the best bound possible using this formula. One thing we can observe about this is that this value is invariant under translation and or scaling. So to make our life easy, we can therefore focus on a polynomial such that a polynomial that is monic and without a constant term. We can consider a monic polynomial without a constant term. Right, so if you look at, for the case k equal to 1, a monic polynomial without a constant term becomes this. So we just need to make sure that we have, with this, p of lambda 1 is greater than lambda p already. So p of the optimal polynomial with just this linear term here, x. And so with all the other relation, we get back to the Hoffman bound, which we already showed about. Now, what about for k equals 2? We are looking for alpha. So basically, so we are now looking at this polynomial, x squared plus bx. So it really has to do with getting the best b possible. That will help us to get the bound, right? So in that same paper, it was discovered that if we choose b to be minus theta I plus theta I minus 1, where theta I is the largest eigenvalue such that theta is less than minus 1, then that gives us the best possible polynomial for k equals 2. And therefore, the bound becomes this. Indeed, you can't do better than this. This is actually the best possible polynomial. Can you get another polynomial that will give us the same value? Yes, there could be more than one polynomial, but in terms of the eigenvalues, this is standard, right? So now, I don't want to go through the proof, which it's a little bit, yeah. So, so it's more of optimizing this, right? So optimizing everything with relation to, yeah. So we are still on the quest for getting a polynomial, a closed form polynomial for the general k. So the authors suggested this polynomial as one of them, and of course, they did not say that it gives the optimal polynomial. No, it is not the optimal polynomial. So if we consider this polynomial, then the k independence number, if k is odd, then this polynomial is strictly increasing. So the lambda p, the smallest, the eigenvalue that gives us the smallest p of x is the smallest eigenvalue, that's theta d. And so lambda p is at p of theta d, and then the bound becomes this. Observe that one of our main challenges is this term over here. And that applies to everything because we need to evaluate p of a, and then now take the largest value on the diagonal. So this is always a problem. If k is even, it was shown that as k approaches infinity, the minimum approaches minus half. So this polynomial, the minimum approaches minus half. So the bound tends to be this. All right. So like I said, this polynomial is not optimal, and it was also not claimed to be optimal. So basically, our goal is, well, can we get an optimal polynomial for k equals 3, for k3? But recently, Shanna was here. She gave a talk on this work. I was part of this seminar when she gave the talk. So there was a follow-up paper where they obtained the best polynomial by solving a given linear programming problem. So basically, I think it's a nice paper. If you are interested in this, please, you have to look at that paper. So basically, if you give me a graph, any graph at all, yeah, I solve for, and you give me the eigenvalues for that graph, we solve for the linear programming problem, and it gives us the best possible polynomial because it's optimization. So we get the best possible polynomial. And with that, we are able to use to find the bound on alpha k. All right. And in this talk, our focus is getting a closed form formula. Right? We want to get a closed form formula that we can always use. So we want to look at for k equals 3, the polynomial for k equals 3. Now, what it means is that we are looking at, we have two parameters here, b and c. Right? We are to optimize this over b and c. And one thing we may also need is the fact that we need to know where the minimum is occurring. And this is a k polynomial, so the minimum can vary very fast depending on our choice of b and c. So what are we going to do? We'll look at this lemma. First of all, it's a very lengthy lemma, but I'll explain that briefly. So basically what this lemma is telling us is that, well, to get where the minimum occurs at any point in time is difficult. So why don't we fix b? Let's fix b. Give me b fixed, and then c is varying. Let's define t to be a least integer such that the minimum does not occur at theta L. Right, so for all c, and then we define ci star to be the solution of the linear equations p of theta equals p of theta I. So we are looking at where each of these meet, p of theta I and p of theta I plus 1. And we define ct to be where p of theta t equals p of theta d. Basically, we are interested in these intervals, right? So what this lemma is telling us is that if I choose c to be in any of these interval, I know that the minimum is going to occur at theta I. So the minimum lambda p will occur at theta I if I choose c to be in a particular interval. So if I choose c to be in this interval, these are c value. If I choose c to be in the interval id, then the minimum is going to occur at p of theta d, right? The smallest eigenvalue. In other words, theta I minimizes the polynomial p over the set of eigenvalues if c happens to be in I of c. Yeah, this is useful because in our proof, we are going to then be able to track where the minimum occurs at for various values of c. Right. So now our focus is to get the closed form formula for k equals 3. So in our work, we define S to be everything is the same. We are looking at the regular graph on n vertices with adjacent symmetries is this, eigenvalue is this. Let S be the largest index such that theta of S is greater than this value, theta minus of theta naught plus theta naught theta d. Theta naught is the largest and theta d is the smallest eigenvalue. Permit me to call this delta. So this delta is actually the largest eigenvalue on the diagonal of the A cube matrix. This is precisely twice the largest number of triangles on any vertex in G. So if we discover that if we choose B to be this value, minus of theta s plus 1 plus theta d, and C to be this, all these are eigenvalues, theta s plus 1 d. Then our optimal polynomial is given by this. The optimal polynomial for k equals 3 becomes this choice of values for B and C. And therefore, the corresponding 3 independence number becomes this value. Right. So basically, the main thing here is getting our B and C. And let's remember our theta s is the largest, s is the largest index such that theta s is greater than this. Now, what happens is that if this graph happens to be a bipartite graph, then indeed, because theta d is just the negative of the largest eigenvalue, and there are no triangles, theta s happens to become the least eigenvalue greater or equal to 0. And so the bound just reduced to something very simple. And the B and C are still the same. right? So let's just look at a quick example of this before I comment on the proof if we have some time. Actually, the proof is very lengthy. The proof of the lemma is like 2.5 pages, and then the proof of the matrix is like almost 6 pages. So I can just talk a little bit about that. Yeah. So if we consider this antipodal bipartite distant regular graph of degree d and diameter 3, then the number of vertices in the graph is 2 times d plus 1, and it has these eigenvalues. Since the graph is bipartite, we have no triangles, and theta s becomes 1. So b is d and c is minus 1. So if we just substitute this into the formula, we get alpha 3 to be less or equal to 1, which is, so alpha 3 is precisely 1, which is expected because the graph is of diameter 3. So we expect that it should have alpha 3 to be precisely 1. So let me just look at some few graphs and what their parameters b and c are. So for instance, this refers to the Johnson graphs. So the Johnson graph 7, 2, 8, 4, and 14, 7. So theta s happens to be 3, 2, and 5 for each of these. And then we obtain b to be 1, for instance, for the J2, J7, 2, and c is 1. And this gives us 1 as expected. Right? For the cube graph, 8, cell graph, and the cell 120 graph, the Blender graph, and then the odd graph, we can do same. And then the bound gives us, for instance, for the odd graph, the bound gives us 8. And then the Lubnian graph, we get 80. All right. So in the next, so like I was saying earlier, the issue has to do with the W of P. So for instance, in this case, if we know that the graph has get greater than 3, then we don't need to even worry about the triangles because there are no triangles in that graph. And so everything reduces to this. It becomes as simple as this, and the formula also reduces very simply. All right. So let's look at a quick comparison. Here, I'm going to be comparing it with so if you consider this polynomial, and then this our parent polynomial s cubed plus bx squared plus cx, where b and c are what I stated earlier. These values. So and this has to do with the actual alpha 3. So apart from some few of these graphs in here, most of the graphs are all named graphs in Sage. So we use Sage to calculate these values. So we see that, well, this bound performs extremely well. So for instance, if you look at the Johnson graph, we have 26, and this is 19, 140, this is 16, 141, this is 21, and it's almost throughout. So if we now compare it with the original values, we see that there are on few occasions where there's a difference as expected because the independence number is NP complete. So we see that we have some, my computer couldn't calculate it. Yeah, so we have some cases where we have some differences, like things like this. Okay, yeah. But in most cases, we see that the values are very close. In fact, they are close and they are equal in most cases. And in fact, for all named graphs in C, the same pattern continues. So that tells us that, yes, indeed, that polynomial does a very excellent job. And in fact, that's the best possible. We can't do better than that. And like I said earlier, can we get another polynomial that will give us the same value? Yes, we can. For instance, if you look at the follow-up work that Ada and Shana gave the presentation on, there are some cases where the values coincide with this, and the polynomials are different as expected, right? But you can't get any polynomial that would do better than this, than what we have right now. Okay. So a bonus this year, as also stated in the original work by Ada, is that we are able to get a bound on the diameter of the graph if using this approach. So for instance, with B and C, if we find that the independence number alpha 3 is a value less than 2, basically what this tells us is that the diameter of the graph in question has degree at most 3. Right. So now let me go back a little bit and comment slightly on the proof idea. Okay, so what did we do? Basically, we look at omega alpha, the bound, and then now the bound is now a function of B and C. So we have B and C in the bound, and we don't know which one we are choosing. At the same time, we don't know where the minimum occurs at, because we need to know where the minimum of the polynomial occurs at. So it's like now we have 3 things we are working at: where the minimum occurs at, what the B is, and then what the C is. So the first thing to do is we fix B using the lemma. We fix B. We consider B as a fixed value, and then now try to optimize the polynomial P of x equals x cubed plus bx squared plus c. So B is fixed, and so now we are trying to look for the best C possible. So with that, we now optimize that polynomial, the bound, holding B constant. And so we are able to trace where the minimum occurs at because of the lemma. And then we obtain the optimal C, the best C possible. And that C, the best C possible, is now a function of our B. So we've not lost track of our B. So now with that, we now go back and put the optimal C into the bound again. And then now the new bound is just a function of just one parameter B. All right, so the alpha 3 is now a function of just B, because initially we started it as a function of B and C, and then we fix B, and then now optimize this as a function of C, right? As a function of C. And basically as a function of C, what I mean is that we look for the optimal C that optimizes the best C that optimizes that bound, and it's also a function of B. So we now go back and put that formula into alpha 3, and then we now have a bound in terms of only B, and then we now optimize this, right? So in that process, we are able to get the best B and C possible by just going back and forth from that two relations. All right, so I'll end over here if there are other questions. The proof is not on the archive yet, so if someone is interested later, I can share it. Yes, thank you very much.
Thank you. Are there questions? I have one to start, if no one's going to jump in right away. So you gave several different bounds. Do you know what happens with any of them when the bound is tight? Like, can you characterize anything?
So if the bound is tight, then what that tells us is that we are able to, well, I didn't actually mention that. So then we have tight interlacing, and basically what that tells us that we are able to trace even the eigenvalues for how do you call it, the main matrix, the eigenvectors for the large matrix. So we have, I didn't really talk about that, the equitable partition. Basically what it means is that now we have an equitable partition. Yeah. Mm-hmm. Yeah, if the bound is tight, then we kind of have an equitable partition.
Thank you.
Can I ask a question?
Yes, please.
Sorry, there's some noise in the background here. Can you go back to your table where you've got all of your bounds?
Okay.
Like, I was surprised at how often the bound is really good. Yeah, this one. Are you using, when you put your polynomial in the ratio bound, do you have to take a floor to get your upper bound, or are you getting integers in your bound? Do you know what I mean?
Okay, so if I understand your question, you mean when we put our B and C into the bound, Do we
Yeah.
get integers or floats?
Yeah.
Oh,
Do you get,
yeah, okay. Yes, so good, yeah, very good question. So I actually, yeah, I didn't mention that. So so for those places where I have, if you see dots, it's kind of small.
yeah, I was wondering if that was it.
Yeah, if you see dot, it means there's some small float after that. Yeah, and where there's no dot, it means it's a precise value. It's an exact value, yes.
And do you have any sense of what's going on with the examples where you don't get a tight bound? Like, is there something going on with the graph that makes the method not work?
When you say tight bound, you mean when we have float values?
No, I meant like where the bounds are higher, like where you've got.
Oh, yes. Yeah, that's a good question. So for instance, an example is this. Or if you look at the Meredith graph, we have the bound is giving us 8, and then the original bound should be 7. Yeah, so, well, I did not really investigate that. I just thought, okay, well, so this is, maybe, you know, yeah, maybe it's a good question. I should be investigating why we are having differences, right? But the thing is that the bound itself, the original bound, which we are trying to optimize, is not always tight, right? The original bound we are trying to optimize and get the polynomial for. Yes, this is not always tight, right? So the best we can, because since this is not tight, we can't be assured of getting a polynomial that will make it tight. If it's tight here, that's good. Yeah, but basically I also start from this portion, right? But indeed, one can also investigate why, you know, for instance, W of P right now is kind of, we've lost some value. This is kind of large, right? Because the original thing that should be here should be the diagonal, the largest value on the diagonal of the independent set. But we've ignored that because it's difficult to get the independent set. So we've taken everything, the entire thing. So sometimes this guy is larger than expected, right? The W of P is larger than expected. So this also affects the bound in a way. Yeah. Thanks for that question.
Yeah,
Nice.
thank you.